What do we do if he doesn't show up?
Dr. Dabney, do you have any suggestions?
So it's being recorded, right?
Yeah.
Yes.
Yeah, so I would say press on, because everybody else has got other stuff to do. So just go ahead and do it, and if he joins during it, fine, if not, he can just do the recording.
Okay, so we'll get started. That's good. Okay. I am going to start recording. Okay, good afternoon, everybody. So today I am pleased to present Eric Whiting for his defense. He's been working on his thesis very diligently over the summer or before in spring. So, even with COVID and all of us, getting overwhelmed, he is worked very diligently on it. So we are here to see what he's done and have him graduate and go wish him good luck for his next journey as a PhD student. I know Eric since spring of 2019. He has taken 2 courses with me, which is Engineering Software 1 and 2, and he has been a very good student in my class. He's been very attentive and serious about his studies. So let's all welcome Eric. And Eric, it's up to you now to go ahead and get it started.
Okay, cool. So I'm going to go ahead and share my screen. And you guys can all see my PowerPoint as the whole screen, right? Good? Just thumbs up, Dr. Dada, if I'm good. Okay. All right, so thank you everybody for coming. Like Dr. Dada said, my name is Eric Whiting. This is my thesis defense. My thesis is performance testing and agile software development. This is some more official information about my thesis if anyone's interested. Today I'm going to introduce the problem by talking about what is Agile, talk about what is performance testing, and then the challenges that come when you try to put performance testing in Agile. I'm going to talk about the study that I did, which included the literature review to kind of identify some of the problems and get an idea of where I wanted to go from there. The literature review, I'll talk about the steps that we took, the findings and everything. I'll break once for questions after there's going to be two question breaks in the presentation. Once after I talk about the literature review, and then I'll talk about I developed a software framework called LULU Performance Test that applies some of the stuff I found in the literature, and I'll demonstrate that, and I'll talk about future work and break for questions again. And if there's time, acknowledgements. Okay, so to understand what Agile is, we have to understand what the SDLC is, and the SDLC is a software development lifecycle. Anytime that you're developing software for a user base, whether it's consumers, customers, or internal customers, there's 7 phases that you go through. There's requirements gathering, where you figure out what kind of problems your potential users have. There's the analysis phase, where you analyze those problems and you think about how you can fix them or address them. There's a design phase where you think about how you're going to develop a system to solve those problems. And then there's the construction phase, where you actually build the things that you designed. Then there's the testing phase, where you test out the things that you built in the code. Do you make sure that the stuff you built is actually solving the problems that you identified? Then there's a deployment phase, where you send out the software that you created for your users to use. And then there's an ongoing maintenance phase, where you do stuff like software upgrades and any bugs that come up. And depending on what source you read, some of these are considered, some of these will be put into their own phase, like analysis and design is sometimes considered 1 phase. Other places consider it 2 phases. It's not important. Mostly these phases are what you do when you're developing software. So the first way that we usually implement the SDLC is with the waterfall model. This is where we do each phase in its entirety before we move on to the next phase. It's kind of considered the old way, but it's still relevant. And you still see it mostly in mission critical software systems, which is like software that runs life support systems or rockets or jets or something like that. And basically, the waterfall method, we do everything that we're supposed to do in one phase before we move on to the next phase. So an example is before we move on to the testing phase, we code the whole system, we build the whole system. And before we even start building the system, we design the whole system, we design the database schemas, the class diagrams, and all that stuff before we even think about writing code. Now, alternatively, there's the iterative model, which is the official name of what we call Agile. The iterative model of software development is when you take a few requirements at a time and you take it through those phases. You find maybe 1 or 2 features that you want to build, and you design those, you develop them, you test them, and you deploy them. You get feedback from your users, and then you repeat the whole process over again. That's the iterative model. It's what we call Agile. Agile covers a few different methodologies that you see listed here. Kanban and Scrum are probably the most common. I do Kanban at work personally. Agile has a lot of benefits. The main benefit is that you can react quickly to shifts in the market demands. So in the waterfall method, you design a whole system and you plan out an entire system before you start building it or deploying it. And sometimes you end up developing a system that is going to be irrelevant by the time you're done with it. So Agile kind of addresses that problem by allowing users or allowing teams to just develop a little bit of the system at a time. So if the system needs to change, it's not so expensive that you can develop new features. It's not so bad to change directions, basically. To do Agile properly, there's a few things you have to do. You have to have really good communication between your teams. So the developers and the business teams, they have to have a good means of talking to each other. You have to be comfortable with experimentation. And most importantly, you have to have really good testing. So we want systems that we build in Agile methodologies to be well tested, so that if we do have to shift focus or change things or experiment, we have a good test suite that tests the software and makes sure that we haven't broken anything. And that's really important when you develop Agile software, is having good testing. Software testing, there's a few different kinds. There's unit testing, where we test different methods in the code or classes. There's integration testing, where we test different components and we make sure that they play nicely together. There's functional testing, where we test out a feature. So something like logging in and seeing your emails, for example, that's a feature, and that's what would be a function test. Then there's acceptance testing, which is where our users test out the system that we build, and they say, yes, this is what we want, or they say, no, we need you to fix this. And then there's performance testing, which tests actually how the system like physically performs. Is it fast? Is it robust? Does it respond to requests very quick? So like if I click the login button, if it takes a long time for me to go from clicking login to seeing my messages, that's something that performance testing should catch. Software testing in Agile is kind of unique. There's an Agile quadrant here that was developed by a guy named Brian Merrick and then made a little bit more popular by Janet Gregory and Lisa Crispin in their book Agile Testing. And basically in Agile, there's 2 axes and spectrums on each axis that help us think about testing. There's team supporting tests, which are tests that will make sure that the code is working and that your infrastructure is working. And there's product critiquing tests on the other end of the spectrum, which are making sure that the product is doing what it's supposed to be doing according to the users. And then on the other axis, there's business-facing tests and there's technology-facing tests. So in quadrant 4, the bottom right quadrant, we have performance testing. So this is testing the actual technology that we have, so our servers and our databases and our networks, and it's critiquing the product as a whole. And that's where performance testing falls. Performance testing includes a lot of different kinds of testing. There's load testing, it's very important to understand load going forward in this presentation. So load is just what we call the number of simulated users using our system. So if I'm doing a load test, that means I have 1,000 fake users using my application or my system, and I'm recording whatever metrics I want to look at. I want to look at CPU usage or how fast the system responds to something. That's load testing. There's stress testing, where we just keep increasing the load when we're testing the system to see what happens when we keep increasing the load. There's spike testing, where we have maybe 500 simulated users, and then all of a sudden we have like 10,000 simulated users, and then go back down to 500 and see how the system responds to that. Endurance testing is when we do a load test for a long period of time to make sure that the system handles that. And then there's scalability testing, which is where we test and see that over time, if our system can handle more a growing number of users or a declining number of users. This is especially important in cloud development, where we have horizontal scaling sometimes, where if X amount of users start using the system, a new database server gets spun up or a new application server gets spun up, and that's what scalability testing is. And then there's ility testing, and this is when we test a bunch of system attributes that end with the letters ility, like scalability, usability, security falls under ility testing. This is kind of a colloquial term in Agile circles. We call it ility testing sometimes. And so performance testing is very challenging because it's very complicated, because we are testing how our software is making use of our hardware components, and this can get pretty complicated, especially since those are really two different kinds of disciplines too, software and hardware. And because it's complicated, it tends to be very expensive, and running load tests is very time consuming. So when you put all those things together, you have a very expensive process of doing performance testing. And performance testing is especially challenging when you're doing Agile development, because Agile requires you to have quick release cycles. When we build features, we want to get them out to our users quickly to get feedback from them. And performance testing, because it's time consuming, isn't really conducive to that. Another thing is, with Agile development, our systems are never really done because we're only building a few features at a time. We're never really like done building a system. But when you're doing performance testing, you kind of need a completed system, because if you only have a system that's running at 50% of what it's supposed to be running, you're not really getting accurate results from the performance tests. So these are some of the challenges of doing performance testing in Agile. So I wanted to address some of the problems by building some kind of software system that would try to find some of the challenges in performance testing with Agile. And in order to do that, I had to first do a literature review. So for the literature review, what we did, and when I say we regarding the literature review, I mean myself and Dr. Dada, because she helped me a lot with this. So the literature review is basically a reproducible analysis of the peer-reviewed research that's out there already. And what you do is we defined the thing that we wanted to learn about, in this case was performance testing in Agile, and then we read all of the articles that come out from searching the different databases, and we decide if they're relevant, and we start analyzing the data that we find in there. And the goal was first to contribute to the current research, and then also to use the information we find to develop an application that would help with these problems. So the literature review, what we did was gather about 5 years of research from January 2015 to December of 2019 related to performance testing in Agile, and I'll talk about the search terms in a little bit, and from the peer-reviewed research. So we searched the IEEE Explorer database, the ACM Digital Library database, and the Web of Science database. I should note that there were no results from the Web of Science database, but we did search it, so I did include it. And when we searched those databases, we used these terms that you see on this slide right here. The Agile terms I got from a paper that we were reading that was another literature review of something else Agile related. And these were the these were the search terms they used for Agile. So I figured if it was good enough for them, it's good enough for me. So these are the terms that I used to search the databases for Agile. And then I did an and search in the databases with these performance testing terms. The performance test terms I used was performance test, non-function test, and NFR test, because performance testing is also called non-functional requirements testing. And so I included that in the search terms. After we got the results, I filtered it by that 5-year time span that I mentioned earlier, from January 2015 to December 2019. And then I filtered it again to only get journals and conference papers. So the IEEE and ACM databases, they sometimes return magazine articles. And even though it's an ACM magazine, it's not as authoritative as a journal or a conference paper. So I just ditched all of those. We're only looking at journal papers and conference papers. And then from those results, we did a quality review. And what we did was there was a title review, an abstract review, and an article review that myself and Dr. Dada did. And there's the process is diagrammed here. Basically, so for example, for the title review, I would read the title of one of the papers and decide there if it was going to be relevant to the study or not. And then Dr. Dada would do the same thing. And if we agreed, we kept it and it went on to the abstract review, or we both agreed that it was no good and we threw it out. And then once we did the quality review, we ended up with 39 papers from the literature review, or for the literature review. We started with 117. That was how many results we got when we did the search in the databases with the different search terms. But after the title, abstract, and article reviews, just 39. So the results that I'm about to talk about are from those 39 papers. So one of the first things that we noticed from the paper from the literature review was 3 of the 39 papers were also literature reviews. 14 of them were just regular reports where they talked about where a team or a researcher talked about maybe a team tried to implement a new process of performance testing or some other kind of testing in Agile, and they just wanted to talk about it. But the majority of the papers were solution papers. They were papers that recognize that there is some challenges for performance testing in Agile, and these are solutions that these papers are proposing for those challenges. So it seems like solution papers are kind of going up, are getting more popular in the last 4 years. When we analyzed the articles, it seemed like the solution papers, they fell into a few of 7 categories. So the papers that presented a solution, they could be one of any of these kinds of categories you see here. So there's model-based testing solutions where we kind of model our system so that we can simulate tests and see how the model performs and assume that that's how our system will perform. There's visualization-based solutions, which is where instead of doing tests, we give developers a new way to think about performance testing and how to see it, and hope that helps with performance testing. There's load manipulation-based solutions, which was the most popular in the research, and this is different ways of defining or configuring the load when we do performance tests. There was one paper that mentioned fault injection, and I'm going to talk a little bit about that paper later, but that was basically just intentionally making something fail in our systems to see how our system responds. A lot of solutions presented domain-specific languages, or DSLs, and these were always in conjunction with another kind of solution. So for example, a lot of times a solution was a load manipulation solution that was configured with a DSL, but DSLs were never presented alone. There's also test automation solutions and CI/CD solutions. CI/CD is continuous integration, continuous deployment, continuous delivery. And this is something that's really common in Agile, and it's a way for developers to kind of all come together with their code and make sure that someone else's changes aren't stepping on somebody else's changes. And a lot of the solutions in the research deal with extending CI/CD. This is kind of an attempt at showing a trend in the solution types, but statistically speaking, there really isn't a trend. All we can see is that load manipulation and CI/CD solutions are consistently popular when we're trying to solve performance testing problems, and that everything else is just kind of sporadic. And then also in the literature, besides the solution types, we also see a lot of problems that are repeated, or there's a pattern that we see certain types of problems in the literature. Most often the problem that we see is cost, time, and complexity, but here's a list of some other problems that are in the literature, but they're not really important. So and here's a kind of a quick visualization, but the important thing to note from the types of problems we have is that complexity, time, and cost comprise 68% of the problems mentioned in the literature about performance testing in Agile, and so that's probably the biggest problem that needs to be addressed. It seems like complexity is actually trending down, and that's another thing I'm going to talk about later. But complexity is maybe starting to be mentioned a little bit less in the literature, but time and cost are being mentioned a little bit more often in the literature. So I want to break real quick for if there were any questions about the literature review before I move on to the software and a demonstration. Does anybody have any questions they'd like to ask about the lit review? I went through that a lot faster than I did.
Yeah, I don't have any questions. That makes sense.
Okay. Anybody else? Okay. Dr. Dada, should I move on? Should I wait a few more seconds? Okay. All right, so now I'm going to talk about LULU performance test. So I took what I learned from the literature review, and I decided to apply some of the lessons I learned into building a software system. And I built LULU performance test, which is a performance testing framework. The name LULU comes from a couple of my other side projects that have the name LULU in them, and I want to consolidate them into the LULU family of testing software. But the goals of LPT, which is what I'm going to call it from now on, is I wanted to give users the ability to quickly develop performance tests, to be able to do it in a customizable way with an expressive syntax, and a way to plug it into CI/CD tools. Basically, the way that LULU performance test is going to work is users will give the system a location of automation scripts, and the system, and then also a definition of how many users to simulate for those scripts, and what components we want to monitor while those scripts are running. And then the system is going to tell us how, is going to report those metrics, and then also any error information if necessary. So basically what an automation script is, and there's going to be an example later, an automation script, in case anybody doesn't know, is it's a script that we write in a programming language that's going to simulate users. We can tell the computer to go to this website, click on this link, and expect this. And what we're going to have here in LPT is we're going to have a script is going to represent a user, and we're going to say, I want 500 people running this script, or I want 10 people running that script, and it's going to do that to the system to simulate an actual normal day of usage for that system while monitoring system metrics like CPU usage or memory usage. Here's a really basic high-level architecture of LPT. There's the system has two main components. There's the metric monitor, which is responsible for monitoring the system performance, the CPU usage, disk space usage, anything else that you want to define, and recording those metrics. And there's also a use case runner component, and this is going to take in those automation scripts and use whatever load definition was provided by the users to run those use cases. And when I say use case, automation script, those are synonymous in this case. If you want to look at this this diagram any further, there's the use cases are the right side of this diagram kind of represents how a testing team would divide up use cases, and it doesn't actually have much to do with the actual LPT system, but sometimes testers will divide use cases into user groups. So the people in the marketing team might use the system differently than the people on the accounting team. So that's what user groups are. So also I built a really simple sandbox application to test LPT with. So this sandbox application is supposed to represent a system that somebody might be building in the real world. It's a really simple music store app that has about 2 use cases where you can explore bands and buy albums and look at albums and look at sales history. And that's just to like simulate something that a team would be building while using LPT as a performance testing tool. It has a really simple service-oriented architecture. It just has, I built it with Flask and Postgres and REST API. So the basic usage of LPT is that inside of our application, so in this case, inside of that sandbox application, there's a test harness, and this is normal. So usually when you're building a system, you have a test harness that has unit tests, integration tests, whatever testing stuff you have, and LPT is going to go into that test harness, and it's going to be part of your entire test suite. And what users will do is they'll use the LPT DSL, the domain specific language, for defining the location of automation scripts, the load definition, and what metrics we want to watch. And then what happens is in the system, we're going to have the actual jar file of LPT in the test suite, and in our build script, we're going to call the jar file and pass it the location of the DSL script. Now, this is not the optimal workflow. I am not a Java guy. I don't know how to deploy Java applications, but this is kind of hacky on my part. If I had more time, I would have done this probably a little bit more professionally, but I needed Java for the multi-threading features that it has. So that's why this is a little dirty. Now here's an example of an automation script, just so that we're all on the same page. This automation script is written in Ruby with a library called Waiter, or Water, I actually don't know. But it's kind of self-explanatory. If you look at it, basically this script tells the computer tells the program to go to this website, click this link, randomly pick an album, click on it, go to this other link, randomly click on a band, and then close the browser. And that's what an automation script looks like. This is not to be confused with an automated test, because in an automated test, there would be asserts and we'd be checking for something. But since we're just simulating users, we don't really need to do that for automation scripts. Here's an example of the DSL script that you would use with LPT. You'll notice that it's just JSON. I did not write a full-on DSL with like Antler or something, but this is just a JSON dialect. You can kind of tell what's going on. There's 2 use cases and 2 monitors in this performance test. So we name our use cases, we pass it the location of a script, and we tell it the command that we want to run. And this is part of making LPT customizable. So if you wanted to write Python scripts or Ruby scripts or whatever automation script you wanted to write, LPT will be fine. As long as you can run it from the command line, LULU performance test will run the script that you want to run. So you tell it where the script is, you tell it, I don't know if y'all can see my mouse, but I'm kind of, can y'all see my mouse? Okay, yeah, so you give it the location of the script, you give it the command you want to run, and you tell it how many users you want to simulate running the script. So in this case, I have 2 people exploring bands, and I have 2 people exploring albums. And those are the 2 use cases. And then there's 2 monitors that, in this case, we have a memory and a CPU, and we're gonna monitor the CPU and memory usage every 500 milliseconds, which is every half second. So when we call the jar file and we pass it this script, it's going to run 4 threads with those 2 use cases and monitor memory and CPU every half second. This is an example of a build script that would be used with Travis CI. So I'm going to show you guys a build script in a little bit, but this is part of one. And what happens basically is this is the important line to look at. So we call the LULU performance test jar file, and we pass it the DSL script location, and it's the same DSL we just saw, and it's going to in Travis CI, which is another, basically almost like a cloud, and their own infrastructure. They're going to build the application, and they're going to run this performance test, and you're going to be able to see the results. That's how CI works. Here's an example output. I'm going to show you a more recent output in a little bit when I do a demonstration, but this is how it would look, and basically. So the basic kind of class diagram of LPT is the metric monitors. They both implements two interfaces. There's the runnable interface, which is the Java standard library interface for multi-threaded functions, and then there's the monitoring interface, which is what I created, that has the necessary methods. And then, so metric monitor is an abstract class, and then there's actually 4 concrete classes that extend the metric monitor. There's memory, CPU, and disk space, and those are like, there's kind of built-in ways in Java to monitor those things. And then there's also another monitor class called other monitor, where if you can pass it a system command, like a bash command, that will find that whatever metric you want to look at, you can monitor that too. And I have LPT open if anybody wants to look at that as well. And then also there's an aggregate class called monitors that's just a collection of metric monitor instances. The use case class diagram is kind of the same thing. There's a thing called runnable use cases, which implements the runnable interface. And then there's the actual use case class, which is, so in the last example, in the DSL example, we saw that I had 2 use cases, but each use case had 2 people running it. So in that case, we would have 2 instances of the use case class, and then actually 4 instances of the runnable use case class. And then again, there's a composite class called, or aggregate class called use cases, that was just for better management in the code. All right, so I'm going to do a demonstration now. Okay, so here is this is the sandbox application. This is all running locally right now. I have a bunch of fake data in here that I used a data generator for. There's really no band called the MIDI Heroes of Brazil, but that would be really cool if there was. And so that's the sandbox application, and that's running. This is the project in Python that is that project, right? So like I said, there's a test harness right here, and this is where we put all our test scripts, and there's a very, very basic unit test in this test script, or in this test harness. And I put this in here because there would usually be also unit tests in any project, and I wanted to make sure that in the when I applied this to CI/CD and Travis, that it worked as expected as well. So there's a basic unit test, but the real thing that we have here is the LPT folder that has the scripts, and these are automation scripts, like I talked about. And just so that we're all on the same page, I'm going to show what these look like when you actually run them in just a second. So, and in here is that same DSL we saw earlier. This is just the same definition of those use cases and the runnable use cases. And so let me just kind of show you how this works. It's like this one. Yeah, okay. I'm going to run LULU performance test, and you're gonna see 4 browsers show up in my on my screen here. And it's just going to run through those use cases automatically. And while it's running through those, it's reporting the CPU usage and the memory usage in the console. And it's almost done, almost done. Every now and then it won't close all of the browser windows. So there it goes. Okay, it closed them all this time. So that's basically how it works. It runs those use cases while reporting the those metrics. Now, obviously, in a real world, in a more professional way, I wouldn't be writing those to the console. I'd be recording them in a database or a spreadsheet or something. But this was just to kind of show us what we're working with. Now that was just running locally. Now, in order to apply this into a CI/CD infrastructure, I used Travis CI, and this is a Travis build script right here. Scrolling up and down on your screen right now. And this is, so these are a bunch of commands that are needed to build this in the Travis CI infrastructure. And once it builds all that, it's going to run this command, which I ran a second ago in PowerShell. It's going to run the performance test, and it's also going to run its own unit test, because I wanted to make sure that that still works too. So it's going to run the unit test, and then it's going to run the performance test anytime that I change something and push it to GitHub. So I'm going to change that. I'm going to commit it. And now I should refresh this, and we're going to see, did I push it? Did I push? No, I didn't, sorry. Okay. So now that I'm pushing it, it's going to push up to, GitHub, and it should, this will change in just a second to like a few seconds ago. Yep, 27. Okay, so now that I've pushed it up to GitHub, there's a trigger that's going to, this is travisci.com. Now, now that I've pushed that, Travis has taken that build script and it's going to start building my application. And when it's done, it's going to run that performance test again. And this is going to take about anywhere between 1 and 3 minutes. So I'll just go ahead and show you one that ran earlier. So you can see these are all the build commands. This is where it ran the local unit test that it was supposed to run, that any project would have. And then when it finished that, it did all of this stuff to build the application in its own infrastructure. And here's where it ran LPT, and it reported on the system metrics. Now this ran a lot quicker in Travis than it did locally, because Travis CI is a giant corporation and I'm just me. So that's why there's fewer notes here. And also in a real project, we would have much longer running use cases, obviously. But anyway, so that kind of proves that we can plug this project into CI/CD. And that concludes the demonstration. And we are almost done, I promise. Okay, so conclusion and future work. So to summarize the findings, again, time, complexity, and cost were the biggest problems that we found in the literature review. Most of the solutions are DSLs, load manipulation, and CI/CD, usually all together, and consolidating the solutions as possible. Some of the thoughts I had was fault injection. I thought that there was one paper I read about fault injection, and I thought it was really interesting. And that paper was talking about a technique they were using at Netflix, where they have this thing called Chaos Monkey, and it's an application that runs through their system and their production system and just randomly fails things. And they see how the Netflix system responds to that. And that whole thing is called chaos testing and chaos engineering. And I think that that's really interesting. And I think it's going to get more popular. But in the literature review, there was only one paper about it, so I could be wrong. Also, so I noted that there was a decrease in papers mentioning complexity as a problem when it comes to performance testing. And I have a theory that that's because cloud development has become more popular recently. I think that when you're able to componentize your infrastructure, it's easier to troubleshoot performance problems. I could be wrong about that, but that's my assumption. And also another thought I had was maybe monitoring is more valuable than testing. I wonder if it might be better for teams to see how their systems perform over time so they can locate areas where it started performing badly and maybe think about why that is. Some of the future work I want to do with LPT, so first, some of the successes with LPT was that it was, I was able to plug it to a CI, to Travis CI, which I didn't officially finish doing until last night. And then I made it language agnostic. I don't think I demonstrated this part, but I can pass it. I used Python scripts, but I can pass it Ruby scripts as well, and I can mix and match scripts. So I do believe that it's technology agnostic, and I like to think that JSON file represents that this can be done quickly. As in quick development, instead of building a whole performance test in something like JMeter, we can just write a pretty simple JSON script. Some of the future work I want to do is actually make a real DSL and not just a JSON dialect, and then survey that DSL for expressing this. I wanted to see, I had the goal of having an expressive DSL for LPT, but I wasn't able to test that because I would have had to poll a bunch of developers and testers and see if they thought it was expressive or something like that, and I just didn't have the time. Another thing I'd like to do with future work is persist the results instead of system outing them to the console, actually recording them in a database or in a spreadsheet. I would definitely like to figure out how people actually use Java and deploy Java applications instead of just sticking a jar file in my test harness. But maybe that's how people do it. I don't know. I'm not a Java guy. And then also I would like to somehow get LULU performance test into my other LULU projects. Some of the surprising finds in the literature review was, again, the decreased mention of performance testing complexity. There was another kind of surprising thing. So before we finished the performance test, I had tried to do, or excuse me, before we had done the literature review, I had tried to do a literature review on my own, and I didn't do it very well. I didn't understand what it was, and I ended up reading a bunch of papers from like 10 or 15 years ago. And one of the things that was really popular back then was dynamic load generation, where we use very black magic math to figure out what kind of what load we want to configure for the performance test. But in the literature review that I did in the last 5 years, I didn't see that in any of the papers. So I guess that just stopped being popular. I'm kind of glad because it looked very tricky and I didn't fully understand it. Some of the future work I want to do is I want to look more into chaos testing and engineering, and also see if there is a correlation between the rise of cloud development popularity and the lack of performance testing complexity mentioned in the literature. And then also look into performance monitoring versus performance testing. And here are some of the differences between the thesis proposal that I wrote and submitted a year ago and the actual thesis now. In the thesis proposal, I talked about dynamic load generation. It just ended up not being part of the thesis because it wasn't in the literature. It was really complicated, and when I was thinking about it, it would have been hard to make tech agnostic because a lot of the dynamic generation papers were based on reading through logs, and different systems are going to log different ways. So IIS is going to log differently than Apache, Windows Server is going to log different than Linux. So it would have been really hard to make tech agnostic. I also, in my thesis proposal, mentioned writing a full on DSL, and as I said a few times now, I just wrote a JSON dialect. And then in the thesis proposal, I didn't mention CI/CD, but it ended up being very important, and I applied it to this project. So are there any questions now?
So tell me about the scalability of this process for big projects.
Yeah, so I did not test more than 30 threads on my local computer. I think that I didn't test more than that. I don't know how it would scale if I wanted to do a bunch more, and I'm still a little shaky on threading and how threading works. I don't know like what the maximum number of threads I can run on a computer is. I know that when I play with JMeter, I can simulate 100,000 users, even though logically I only have like 4 cores on my computer. So I don't really know how all that works, but I imagine it's scalable, but you know, I don't know that. I can't say that for sure.
Okay.
Did Dr. Helm ever make it to the?
I don't think so.
Okay.
I hope everything is okay with him. So, any other questions?
I have an acknowledgement
Definitely.
slide too. Did somebody say something?
The Dr. Radley said something.
Yeah, I just said I don't have any more questions.
Okay.
Okay. Can I do my acknowledgements real quick?
So I had a quick question while you
Okay.
was talking about performance testing and compared to Agile. I just had one thing like, okay, so so while Agile, we know we do a part of the project and then test it and kind of deploy it as well, okay? And you say that if we do performance testing, then it's not going to work very well unless we get the whole project going. So, so let's say I keep pending on my performance testing, and then finally, when I am totally done with the project, I find issues with my performance. Okay, there could be that's one possibility, right? So, have you ever thought of, while before we deploy, could we do this performance testing on the small, the little bit of thing that we are deploying? So version 1, before we deploy that, we do a performance test, and then we do version 2. And so maybe finally, when when we finish it, we will know where the hookup is or where the slag is. Will that be a possibility?
I think that's a possibility, and that's why I wonder if performance monitoring would be better than performance testing, so that we can actually see how the system is performed over time. And originally I wanted to do a system that was recording the results of performance testing and graphing them on the time axis of commits. And so if there was a dive in one of the graphs, we could mouse over it and see what was the commit that caused that dive, and kind of see because like you said, we won't have a complete system. So that's why I wonder if monitoring would be better than testing. But yeah, yeah.
Great, thank you. Anybody else? Any other questions? Okay, so go ahead. I don't think anybody has a question. So go ahead.
Okay, yeah, I just have a really quick acknowledgement slide. I wanted to thank my wife for being so supportive. Her nickname is actually Lulu, which is why these things are called Lulu, whatever. I want to thank my parents for being supportive. I believe they're here watching. Same for a couple more family members. My sister and my aunt are watching. Definitely want to thank my professors, especially Dr. Dada, who helped me a lot with the review, and Dr. Dabney and Dr. Helm, who's not here. I know we haven't talked a lot, but I've seen some of y'all's previous work, so I figured it would be great to have you guys advising on this. And she's definitely not here, but I wanted to thank Dr. White, if she ever sees this, because she helped me get my first publication. So yeah, those are my acknowledgements. Oh, and quick reference slide. Cool.